This lesson has been developed in the framework of SCILED project. Module 3, Footwear Design Engineering, Unit 3, Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lesson 3.5. Managing Fitting Aspects. This lesson is structured as follows.
Introduction. Key dimensions of the human foot. Fitting criteria for selecting elasts. Interaction between foot and footwear upper components. CAD/CAE tools for fitting assessment.
Introduction.
Understanding fitting requires to understand the geometry of the human foot, and then the geometry of a piece of footwear is related to the geometry of the last. Fitting is either managed as an issue of least deviations of the geometry of the foot from the geometry of the last, or as an issue of least deviations of the geometry of the foot from geometry of the final footwear. Both approaches are used in industry.
Key dimensions of the human foot.
Sizing systems have as a starting point either the geometry of the final footwear, for example the new Japanese sizing system, or the geometry of the last, for example European, English and US systems. Lasts take into account the geometry of the foot, though there are also fundamental differences between them. The anthropometrical measurements of the human foot are related to key lengths, widths, heights, circumferences, and angles. The development of the Brannock device made a huge impact on the foot measurement and sizing field. The projection of the longitudinal axis of the foot on the Brannock device on the plantar surface of the foot when the heel area is fixed on the instrument as instructed is called the Brannock axis, and it is used in most relevant anthropometry studies. The key dimensions of the human foot are 1. Foot length. 2. Arch length. 3. Heel to medial malleolus. 4. Heel to lateral malleolus. 5. Heel to fifth toe. 6. Foot width. 7. Heel width. 8. Bimalleolar width. 9. Midfoot width. 10. Medial malleolus height. 11. Lateral malleolus height. 12. Height of 50% foot length. 13. Ball girth. 14. Instep girth. 15. Long heel girth. 16. Short heel girth. 17. Ankle girth. 18. Waist girth.
Fitting criteria for selecting lasts.
The description and definition of relevant terms is as follows. 1. Front point of the last bottom. 2. Bottom support surface, tread point. 3. Back point of the last bottom. This is the center point of the intersection line of the front upper and bottom around the heel. 4. Maximum point of heel curve. 5. Back point of top line. 6. Front point of top line. 7. Toe depth. The height of the big toe tip point. 8. Ball girth. The girth of the contour though the points of the first and fifth metatarsal phalange joints, 25 and 26. 9. Instep girth. The girth of the contour though the waist point, 27. 10. Heel girth. The girth of the contour though the front point of the top line, 6, and the back point of the shoe last bottom, 3. 11. Width of top line. 12. Length of top line. 13. Distance from the toe end point to back point of the top line. 14. Last toe allowance. The distance from big toe tip point to the front point of the shoe last bottom, 1. 15. Toe spring. The vertical height between the front point of the shoe last bottom, 1, and the ground plane. 16. Room around heel. The projected distance between the back point of shoe last bottom, 3, and the maximum point of the heel curve, 4. 17. Heel elevation, heel height. The vertical distance between the back point of the shoe last bottom, 3, and the ground plane. 18. Heel height. The vertical distance between the maximum point of the heel curve, 4, and the ground plane. 19. Back height. The vertical distance between the back point of the top line, 5, and the back point of the shoe last bottom, 3. 20. Longitudinal axis of shoe last bottom, side view. 21. Curved line from front point of shoe last bottom to front point of top line. 22. Top line. 23. Big toe contact point. Corresponds to the salient point of the big toe on the foot. 24. Little toe contact point. Corresponds to the salient point of the little toe on the foot. 25. The first metatarsal phalange joint, MPJ. Corresponds to the first metatarsal phalange joint of the foot. 26. The fifth metatarsal phalange joint, MPJ. corresponds to the fifth metatarsal phalange joint of the foot. 27. Waist point corresponds to the salient of the lateral base of the fifth metatarsal. 28. Inner width of the big toe. The width between the big toe contact point. 23. And the longitudinal axis of the shoe last bottom. 20. 29. Outer width of the little toe. The width between the little toe contact point. 24. And the longitudinal axis of the shoe last bottom. 20. 30. First metatarsal phalange inner width. The width between the first metatarsal phalange joint. 25. And the longitudinal axis of the shoe last bottom. 20. 31. Fifth metatarsal phalange outer width. The width between the fifth metatarsal phalange joint. 26. And the longitudinal axis of the shoe last bottom. 20. 32. Outer width of waist. The width between the waist point. 27. And the longitudinal axis of the shoe last bottom. 20. 33. Width of heel area. The width at the central position of the heel area. 34. Heel centerline. The vertical bisector of the heel area. 35. Shoe last bottom outline, last bottom pattern.
Interaction between foot and footwear upper components.
Footwear has always an intended use, whether it is simple comfort at home, walking, running, working in an industrial environment, etc. Certain applications may require a looser or tighter fit. The designer needs to identify any requirements for loose or tight fit and select, or modify, lasts accordingly. For example, boots tend to have a loose fit at the toe box and certain sports shoes a very tight fit at the heel area. Tight tolerances practically do not exceed 2 mm. Beyond that value, the user experiences compression of the tissues and discomfort since blood circulation is disrupted. There is a wide pool of lasts covering most applications and sizing systems around the world. In practice, most industries resort to last modifications and trial and error fitting trials until they achieve the desired results. The modern designer needs, occasionally, to resort to the use of fitting assessment CAD/CAE tools that either match the foot to the footwear or the foot to the last. Most of these tools that are in high technological readiness level are purely geometric, based on the use of cross-section evaluation algorithms. Besides assessment tools, there are also design tools, in particular free-form deformation CAD tools that allow for deforming the lattice of a footwear model to match the model of a foot or last. This can also be used for matching foot models to last models. One of the first tools for assessing the fitting of a footwear last in a CAD environment was presented by Azariades et al. 2007, as part of the Virtual Shoe Test Bed project. In this approach, a set of shoe last measurements are compared with corresponding foot reference values obtained from anthropometric surveys. Luxemone, 2001, and Wang, 2010, have also proposed geometric approaches based on comparing girths and other critical dimensions. The mechanical approaches are based on finite element analysis, multiple regression and other models. Compared to geometric approaches, they are more advanced and require knowledge of analytical techniques not in the realm of most footwear professionals. They are also quite demanding in terms of time and effort required to build individual FE models of the entire shoe and human foot, which unfortunately are not yet parameterized to support a wide usage. Practically, most commercial solutions that are used by podologists and medical footwear manufacturers and have now made their way into sport goods and apparel retailing are based on 3D scanning and geometrical approaches. The crude retailing systems, for example Nike Fit Measurement Tool, based on smartphone CCD digital cameras, can indicate sizing options for the interested buyer, which is adequate for most purposes.